Hi, and thank you for joining me for this talk. My name is Michalis, and I'm going to talk to you about stateless model checking of concurrent programs that use barriers. So what are barriers to begin with? Barriers, as in, for example, pthread barriers, are synchronization primitives. And these are not to be confused with memory fences, which are also sometimes referred to as barriers. Barriers are widely used, mostly in scientific applications, and what they do is that they ensure that the execution of a concurrent program will only continue after all threads have reached a specific checkpoint. So let's see an example of this. Here, the main thread first executes a barrier init call, which initializes the barrier object B to the value n. It then spawns n concurrent thread, each of which does the following. It first sets a distinct part of the array M to the result of some local computation, and then it calls barrier wait. Now what this barrier wait does is that it blocks the calling thread until n threads have called barrier wait, but where n is the value the barrier was initialized with, not the number of threads. So after n threads have called barrier wait, then all threads that were blocked can resume, and barriers offer the extra guarantee that after all threads resume, the effects of the statements that were executed before all different barrier wait calls will be visible to all different threads. So for example, when this first thread here executes this statement, then the value that it will obtain for M2 will be the value that the second thread calculated, because this calculation was performed before thread 2 called its respective barrier wait statement. So all in all, barriers are very easy to understand. Their usage is straightforward, but if we try to verify a program that uses barriers using a stateless model checker, and I'm going to explain what this is in a second, then the stateless model checker experiences an exponential slowdown. And this slowdown is not actually due to the concurrent nature of the program, but rather it's due to the usage of barriers. Now in this talk, I'm going to show you that we can get rid of this exponential slowdown, and that we've done so with BAM. BAM is a barrier-aware model checker that manages to explore exponentially fewer executions than state-of-the-art stateless model checkers for programs that use barriers. BAM is built on top of the GenMC framework, which is a framework for stateless model checking, and which means that BAM works for a variety of different memory models, so not just sequential consistency, but also other memory models like C11, and BAM is also sound, complete, and optimal. Now in the rest of this talk, I'm going to briefly explain what stateless model checking is and how it verifies concurrent programs, why barriers pose a significant challenge to stateless model checkers, and how BAM surmounts these challenges. So let's get started. The goal in stateless model checking is to enumerate all the interleavings of a program. And stateless model checkers do that because this is exactly how they verify a given program. So for instance, suppose that I have this program here where the first thread is writing 1 to x, the second thread is reading from x, and the third thread is writing 1 to y. And suppose also that I want to verify some safety property for this program, for example, that this read here will either read 0, the initial value, or 1. Now, how stateless model checkers do that is that they enumerate all the interleavings of a program, which are shown here. These are the 6 interleavings, and then validating that each of these interleavings satisfies the desired safety property. And of course, stateless model checkers do that in a systematic manner. They only keep one interleaving in memory at all times, but the number of interleavings is exponential, so this clearly doesn't scale. So what usually happens is that stateless model checking is combined with another technique that's called partial dereduction, which is based on the observation that we can group interleavings with similar behavior into some equivalence classes. So for instance, for this program here, we can have these two equivalence classes, and in this first equivalence class, if you notice, the read of x is executed before the write to x, while in this second equivalence class, the read of x is executed after the write to x. In some sense, this write to y is irrelevant to the program, as the only thing that matters is whether this read of x is executed before the write to x or vice versa. So if we have these equivalence classes for the interleavings of a program, then instead of enumerating all of the program's interleavings, we can verify it just by enumerating one interleaving from the first equivalence class and then one interleaving from the second equivalence class. So we can restate the goal of stateless model checking to be to enumerate all program interleavings up to some equivalence partitioning. So the only question that remains to be answered is how to best model these equivalence classes. And we can actually do that very concisely and elegantly using what's called execution graphs. The nodes of these graphs correspond to instructions of the program. So this node here corresponds to this instruction, and it basically says write to x the value 1. The edges in these graphs denote relations between the instructions. So for example, this PO edge here denotes program order. Such edges connect the initialization events to the first event of each thread, and they also connect the events of a particular thread. And these green edges, these RF edges, show where a particular read is reading from. They are called reads from. So in this graph here, this read reads the initial value, 0, and in this graph, this read is reading from the first thread, it's reading 1. Now, if you notice, this graph here perfectly captures this first equivalence partitioning, because in all these interleavings, the read of x is executed before the write to x, so it's going to read 0, just as in this graph. And of course, this graph captures the second equivalence class, so we can restate the goal of stateless model checking once again to be enumerate all consistent execution graphs of a given program. Now, I'm not going to explain how this is done in stateless model checking, but this is in the paper if you're interested in that. And instead, I'm just going to note two things that are going to be necessary later on. The first thing is that, of course, the overhead that stateless model checkers encounter is proportional to the number of graphs they have to explore. And the second thing is that stateless model checkers enumerate these graphs one by one, and they do that incrementally by adding one event at a time to any given graph. So keeping these two things in mind, let's see why barriers pose a significant challenge to stateless model checkers. This is how a typical barrier implementation looks like. We can implement a barrier init function with a single write statement that initializes b to n, and we can also implement the barrier wait function by an atomic block followed by an assume statement. So let's see what these two instructions do. The atomic block first reads the value of the barrier, and if the value of the barrier is greater than 1, it simply decrements it. If the value of the barrier is 1, it resets it back to n, and this intuitively captures the case where the thread that is calling barrier wait is the last one to reach the barrier. In that case, that thread resets the barrier value back to n so that the barrier can be subsequently reused. After this atomic block is complete, then each thread calling barrier wait will reread the value of the barrier, and if the value is not n, which means that not all threads have reached the barrier, then the thread blocks. So basically this assume statement here only allows the execution to continue if this condition here is satisfied. However, this representation is problematic, and it leads to an exponential number of graphs that a stateless model checker will have to explore. And let's see why. Consider this simple program that has these two concurrent barrier wait calls. Using this representation, a stateless model checker would have to explore these two graphs. Now, each barrier wait call boils down to an RMW event followed by a read. This RMW event is a read modify write event that corresponds to the atomic block of barrier wait. And as you can see here, the first thread first reads the initial value of the barrier and then atomically decrements it from 2 to 1. And then subsequently, the second thread resets the value of the barrier from 1 to 2. In this execution, the opposite thing happens. Of course, we cannot have two RMW instructions reading from the same write, for example, from there, because these are atomic blocks, so this would be forbidden. Now, these two read statements in both executions, these correspond to the reads of the assume statements. And as you can see, these reads read 2 in both executions from the RMW that reset the value of the barrier, and this is because this is the only value that these reads can read, which will allow the execution to continue. However, as you can see, this representation leads to an exponential number of graphs that have to be explored. And this is precisely because of the semantics that the barriers have. Due to these atomic blocks, which are modeled by RMW instructions, these RMW instructions have read and write semantics. And because of that, they have to be ordered. And we have to explore all possible orderings for these atomic blocks. And this is why such programs have an exponential number of graphs, even if they have absolutely no data sharing apart from the barrier. And this is exactly the key insight that BAM leverages. The key idea behind BAM is that we can actually treat barrier weights as dummy events. And if we do that, then for a program like this, where each thread calls barrier weights, I'm going to explain the rest of the program in a second, then if we treat barrier weights as dummy events, we can simply enumerate just one graph with these barrier weight calls not being ordered among themselves and be done. However, there is a slight problem if we only do that, and the problem is that these dummy events do not model the semantics of the barrier correctly. So for instance, in this program, after each thread calls barrier weight, then the first thread reads M2, which should obtain the value written by the second thread, and the second thread reads M1, which should obtain the value written by the first thread. However, if we model barriers as dummy events, then no synchronization is enforced. So while in this graph that I've drawn here, this read is reading from that write, there is nothing that actually prevents it to read from the initial value. With the previous barrier representation, the assume statements did that, but now there is nothing that enforces synchronization. So the second key component of BAM is what we call same barrier round relation, or SBR, which is a partial equivalence relation that connects barrier events belonging to the same round, and which the purpose of which is to restore the semantics of the barrier. And SBR does that by satisfying the following conditions, which I'm going to go through in detail now. The first condition says that at most n-1 same location barrier events may not be in SBR. So for instance, if we have the same program as before, and a stateless model checker has constructed this graph, recall that stateless model checkers construct graphs incrementally by adding events one by one, then it's fine to have a graph like this with an empty SBR. But then as soon as we add the barrier event of the second thread, then these two need to form an SBR relation. And this is important because this is going to be in conjunction with the third condition here, and forming SBR is important to enforce synchronization. Now the second condition says that each barrier event either belongs to a fully formed SBR or it has no PO successors. And the purpose of this condition, again having the same program, is to preclude scenarios like the following. Assume that a stateless model checker has constructed this graph, then it should be impossible to, for example, have an SBR containing only one event and then add the read event of the first thread without having added the barrier event of the second thread. This condition says that if a barrier event belongs to SBR, this SBR needs to be fully formed, so it needs to contain n barrier events. Otherwise, such an event should have no PO successors, and this is why such a graph is forbidden. And finally, the last condition says that the composition of PO and SBR and the composition of SBR and PO are part of HB. HB stands for happens before, and this is a synchronization relation that's memory model specific, so it's part of the underlying memory model. So the only thing that's important to know about HB here is that it is a strict partial order. Now this condition has two purposes. First, it enforces synchronization. It basically says that whatever is before a barrier round will be connected by HB. These events will synchronize with everything that is after a given barrier out. Now, the second purpose of this condition is to rule out some badly formed SBR relations. For instance, if we have a program like this, where each thread calls barrier wait twice, then SBR cannot be like this. Of course, we want SBR to have these two barrier events and these two barrier events. And the way we rule out such SBRs, that each of which does have an event, is with this condition that basically says, if we start from this barrier event, take a PO step, and then take an SBR step back to the same event, this will become a part of HB. But since HB is a strict partial order, this graph will be forbidden, and this is how we rule out such malformed SBR relations. Now, we have the full formalism for these conditions in the paper, but I think the key point here is that in order to get exponentially fewer executions while maintaining the semantics of the barriers, we need a relation that restores the correct semantics for the barriers, and in our case, this is SBR. So now, I would like to conclude with some results just to convince you that this also works in practice. These are some benchmarks. We compared BAM against GenMC because BAM is built on top of GenMC. In the x-axis, we have the number of threads, and in the y-axis, which is logarithmic, we have time in seconds. We've set the timeout to 30 minutes, and as you can see, BAM greatly outperforms GenMC. In all cases, GenMC usually times out after 4 or 5 threads. And these two benchmarks are more interesting because apart from the barriers, they have other concurrency aspects that greatly increase the state space, and this is why GenMC usually scales much worse in these benchmarks, while BAM usually manages to finish within the time limit. So to conclude, I've presented BAM, which is a barrier-aware extension to stateless model checking and partial reduction. BAM is exponentially faster in programs that have barriers, and also works on for a variety of different memory models because it's built on top of GenMC. And BAM is available on GitHub as part of the GenMC repository, and we would be happy to receive your feedback.